Hi everyone, today I will be presenting our work towards domain-aware knowledge distillation for continual model generalization. I am Nikhil. I'm currently a PhD student at University of Queensland and IIT Delhi Academy of Research. My collaborator, Professor Mahsa, is from University of Queensland and Professor Chetan Arora is from IIT Delhi. So the overview of current talk is divided into 4 sections. First, we'll discuss about the problem setting and problem formulation. Then we'll discuss about related work in test time adaptation and domain generalization areas. And then we'll formulate the loss function. And then we'll discuss about the experiment section, and then we'll conclude the talk. Coming to the problem statement, the work focuses on out-of-domain generalization. Out-of-domain generalization is a key important component of success of neural networks in real-world applications such as autonomous driving. So this arises fundamentally due to domain shift. Domain shift is a phenomena where training domain and test domain can be completely different. This domain shift can happen due to multiple factors, due to input corruption, adverse weather, illumination changes, adversarial attacks, and sensor malfunction. The goal of current work is focus on only adverse weather and illumination changes. Ensuring robust performance on unseen target domain is pivotal for success of neural networks. The task which we are focusing on is urban scene semantic segmentation. The goal is to classify each pixel into 19 different classes. The current problem statement fits in continual test time adaptation setting, where the goal is to adapt a source pre-trained model which is trained on data to adapt to unseen target domain where the target domain is continually changing. So coming to the problem formulation, as discussed, the problem formulation fits in continual test time adaptation, where we don't have access to source data and target data during training and don't have access to training loss, and we only have test loss and open targets, and the goal is to forgetting elevation. So basically we are trying to elevate catastrophic forgetting directly during inference. So coming to related work, the first work, test time adaptation TENT, is proposed in ICLR 2021, where the goal is to adapt a pre-trained model to data while being received on inference. So TENT adapts the affine parameters of the batch normalization layer to minimize the entropy loss for a particular test sample. Unlike TENT, the current work focuses on a continually changing target environment instead of a static fixed target domain. So domain generalization aims to generalize well on unseen target data. However, current existing domain generalization techniques do not perform well in adverse weather and illumination condition. Current works aim to complement the domain generalization settings by directly adapting to unseen weather target domains during inference. So the proposed approach, we enforce the feature matching between batch normalization prototypes of student and teacher model. Here student teacher model is shown in below, and model theta k-1, the teacher model is shown above. The goal is to enforce the feature matching between student and teacher model to perform knowledge distillation. The current batch normalization prototype should be closer to the domain-specific batch norm prototype in the latent space. So exemplar-based replay buffer is used to elevate the catastrophic forgetting. So we compute the VOG scores for each batch of images and store the most difficult samples based on the VOG score in the exemplar-based replay buffer. And after every couple of iterations, we try to replay these images into neural network so that the model doesn't forget the information of these difficult samples. So coming to overall loss formulation, for each layer, given a mini batch of target data, we compile the batch norm prototype BXT is by compiling mean and standard deviation of each layer and concatenating all these vectors, we get batch normalization prototype of current mini batch. Similarly, we define domain-aware prototype and update it as follows. For samples coming from HT, which belongs to a particular domain, this domain can be a weather condition. For example, fog belongs to a single domain, and night belongs to a single domain. For each domain, we maintain domain-aware prototype PD defined as follows. So coming to the loss function, we define two loss function. One is layer distillation loss function. Layer distillation loss function enforces the similarity between student and teacher model and their corresponding batch nomination prototypes. Similarly, domain distillation enforces for each domain, we would like to enforce batch norm prototypes to be similar to that of the domain aware prototype. Here, beta t k minus 1 denotes the batch domain prototype of domain T. So the overall loss function involves LC cross entropy loss, which calculates the pseudo label based on the teacher model. And then we'll have layer distillation, which enforces batch norm prototypes similarity in the latent space. And domain distillation, for every domain, the batch norm prototype should be closer to that of batch norm domain prototype. So coming to exemplar-based replay buffer, we extend variance of gradients to an online continual setting, and we compute the gradients over k iterations. And based on this, how gradients are changing, we identify difficult samples. And based on VOG score, we identify difficult sample and store them in the database in this replay buffer. And after every few iterations, this exemplar-based replay buffer is replayed into the neural network so that the model doesn't forget the information captured from these difficult samples. So coming to the experiments, we perform the experiments on multiple settings. The first setting is pre-trained daytime models. We take the state-of-the-art daytime models, and we apply this continual setting where the time frame, and we change the weather conditions, fog, night, snow, and repeatedly, and we make sure that the model adapts to these changing weather conditions. We can observe that our approach can significantly improve the performance in terms of different weather conditions and how the model is able to adapt to different settings. For example, on ACDC, the model is able to improve average MOU performance of 4.4%. Absolute. So coming to domain generalization settings, we take the state-of-the-art domain generalization settings for urban scene segmentation, IBM-net, switchable whitening, robustnet, and wildnet. And we apply our current setting on top of existing domain generalization settings. And we can observe that the performance improves significantly. For example, in robustnet, we can observe that around 3% absolute MIU improvements. So coming to qualitative results, given an input image on the night time, we can see that deep lab mobile net performs very poorly and the current existing technique improves. For example, we can focus on the footpath, which is completely missing in deep lab v3 plus mobile net. We can observe that it is getting recovered by applying our proposed framework. So coming to unsupervised domain adaptation methods, we take nighttime unsupervised domain adaptation methods, and we apply our proposed methods on top of it. We can observe that we can see around 2.4% and around 3% improvement in MIU performance. So to conclude, we introduce a novel unsupervised loss function to enforce the feature matching in the latent space between student and teacher models. And this technique can improve the performance of any existing pre-trained model to adapt to changing weather conditions and illumination conditions directly during inference. So this can improve domain generalization of multiple settings, which include daytime models, domain generalization models, and unsupervised domain adaptation models. Experiments are conducted on 6 different weather conditions such as fog, night, snow, rain, cloud, and overcast.